All right, guys. Today, obviously, you guys can see we're going to be talking about heat and temperature. Says, what do you mean? Cut off the foul language. You guys know that foul is another word for a bird. Okay. How to write good. If you want to write good, you have to avoid run-on sentences. They are hard to read. If you want to write good, no sentence fragments. If you want to write good, don't use no double negatives. And if you want to write good, verbs they has to agree with their subject. All right, guys, I'm not an English teacher. All right, back to heat and temperature. So you know that when an object gains heat, the temperature goes up. When an object loses heat, the temperature goes down. We've known that, right, since we were wee little lads, wee little girls. But the question I have for you guys is, does temperature measure heat? For example, right, I'm measuring the temperature in the room, and the temperature in the room right now is about 27 degrees Celsius. Remember, degrees Celsius is the preferred measurement. Am I measuring the amount of heat in the room? That's the question. I want you guys to be thinking about that. Is your answer at this point yes or no? You guys think about it. Let's consider some things. Let's consider an olive foil and a foot pan. What are we talking about here, guys? We're talking about aluminum foil and an iron pan. Okay? Think about this, guys. Here's a scenario. Let's say you're coming home from school, you're famished, and you're just starving, right? So you needed something to eat, but mom, dad, they didn't do shopping. So the only thing that you can see, you can look in the freezer and you find some French fries. You guys ever seen a bag of French fries? And then you know what? There's potatoes on the counter. So you got French fries, you got frozen French fries and potatoes. Now I know what you guys are thinking about the French fries. You're like, oh, I'm going to put those in oil. But you guys, that's all we got in the house. We don't have no oil, so what can you do? You're gonna have to bake those fries. So you put the fries. I don't know if you guys have ever done that. Put it on an iron pan, on an iron baking pan. Most of your pans are iron, right? So you put the fries on there, and then you take your potato. And I don't know if you guys know how to make potatoes. You're gonna wrap it in aluminum foil. So you wrap it in aluminum foil. Then you put them in the oven. Okay, so you put them both in the oven, and then you crank up the heat, right? And you're cranking it up, and you're waiting. You're like, dang, you're getting famished. 15 minutes goes by, 20 minutes goes by. Okay, and here's the question I have for you guys. Let's say 20 minutes. You know what, you're like, you know what, whether it's done or not, I'm so hungry, I'm gonna die if I don't eat. So then you open up the oven, and what do you need? You're like, I need some oven mitts, but you're like, dang, ain't no oven mitts anywhere. So you're like, forget this, I'm just doing it. So let me ask you, if you were going barehanded, which would you prefer to grab? Would you grab that iron pan of fries and pull that out, or would you grab that aluminum foil covered baked potato? Which one would you guys grab? If you guys are thinking smart, you probably should grab that baked potato covered in aluminum foil, because you guys know it's gonna be hot and be like just like that, right? You guys know what I'm talking about, right? But if you grab that iron pan, you're gonna be smelling some burning flesh as your flesh is just melting onto that pan. That's gonna be a lot more hot. So thinking about that, does temperature measure heat? Well, if you guys think about it, you think about which one of those absorb more heat? The aluminum foil or the iron pan? Well, you think about it, didn't they absorb the same amount of heat? Remember, you put them in the oven at the same time. They were at the same temperature for the same amount of time. Didn't they absorb the same amount of heat? Yet there was different outcomes, right? Think about a large pot of water and a small pot of water, right? Let's say you're going to make some hot cocoa, so you want to heat up some water, right? So you put water in a large pot, and you put some water in a small pot. You put them on the stove top. You crank them both up. You guys think about it. After maybe a couple minutes or so, what do you guys think? You're going to go to the large pot, and you might see, you might want to be careful, but even at that point, you might be able to put your finger in that large pot of water, right? But what do you guys think would be different with that small pot of water after a few minutes? That might actually full on be boiling at that point. So what does that tell you? You guys, which one had, so that being those two scenarios, we got to ask that question, does temperature measure heat? Well, think about it, guys. The answer to that should be no, temperature doesn't measure heat. Because you think about this, both the aluminum foil and the iron pan absorb the same amount of heat, yet they were at different temperatures. The iron was at a much higher temperature than the aluminum. That's why it's going to do more damage to your skin. And you think about the large pot of water and small pot of water, once again, both of them absorb the same amount of heat, and yet what will you find? the large pot of water will be lower in temperature than the small pot of water. In fact, if I had to put my hand in it, I would rather put it in that large pot of water than that small pot of water. So the answer to this question is no, temperature does not measure heat. So then that begs the question, well, what does temperature, what does it depend on? Well, if you guys think about it, based on the scenarios, not only does temperature obviously depends on heat. We already know that, right? The more heat something absorbs, the higher the temperature. The less heat, the lower the temperature. But what else does it depend on? Think about it. Doesn't it also depend on the type of substance, right? And also, what else does it depend on? The amount of that substance. So we have several factors. The type of matter affects the temperature along with heat, and also the amount of matter. Okay. So then the question is, what does temperature measure? When I'm getting the temperature of the room in here and it says 28 degrees Celsius, what am I measuring? Well, duh, the average kinetic energy of the molecules in a sample of matter. That's what temperature, I don't say mean duh, because obviously you wouldn't expect me to know that, but it's the average kinetic energy. Now you guys, when you guys think of kinetic energy, I want you guys to think, whenever you guys think kinetic, you guys should be thinking of motion. Kinetic, that's motion. In fact, they actually have watches that are called kinetic watches. You guys know how most watches run on a battery. This one actually is a solar, so it actually runs off light. But there's even more sophisticated that just run on the movement of your body. It stores the energy associated with the movement of your body. That's why they call it a kinetic watch, because it's based on movement. So temperature, what I'm measuring is the average kinetic energy of the molecules in the room. You guys, the molecules in the room are moving. The ones that are moving fast have a high kinetic energy. The ones that are moving slow have a low kinetic energy. When I'm measuring the temperature, I'm measuring the average. I get the average of all the molecules of that sample of matter, in this case the air, is what temperature is. So as you might expect, temperature increases, molecules have increased kinetic energy. And then you guys, if I'm showing this video, what are you guys expecting to see? Hot molecules, cold molecules? When I play the video, we'll see.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one.
You guys, that's kind of like
when the two samples have similar rates of molecular motion, they have reached thermal equilibrium.
That's kind of like on a cold day, right? Sometimes, right? Some of you guys might be cold-handed people, some might be hot-handed people, right? You guys have encountered that. Shake someone's hand, it's like, whoa, it's colder. Somebody might have a really warm hand. Well, think about a warm hand comes in contact with a cold hand. What do we mean by warm hand? That means it has a higher temperature. That means there's more molecular motion. So then that comes in contact with the cold hand, and what's going to happen? Heat is going to transfer from the warm hand to the cold hand until what? So then what happens is the fast-moving molecules in the warm hand begin to slow down, and the slower-moving molecules in the cold hand begin to speed up until they're at the same kinetic energy, the same temperature. So heat's probably the easiest form of energy to collect and measure. So if two objects with different temperatures touch one another, heat will flow from the hotter to the cooler, just like I was talking about with the hands, until they're at the same temperature. So you guys, the physical universe, there's two things that make up the physical universe, matter and what? So you guys remember, matter is anything that has mass and takes up space. Pretty much everything you see around you is matter. What else does the physical universe consist of? Some of you guys know it. It consists of energy. And energy, heat is the most abundant and easiest to collect. So this unit is called thermochemistry, referring to heat as it relates to matter. So heat, you guys, if we're going to measure heat, we have to have units. Here's a typical unit we can use is calories. You guys see, and that's one that we're kind of familiar with. Now that is slightly different than food calories. You know what, in fact, I'm going to bring that up. You guys just make a note here. Or you know what, I'll talk about that here in a little bit. There's also a more common use internationally is for heat is joules, and that's named after this guy who was a brewer, made some beer. Don't worry about the trivia there, but realize it's joules. There's a conversion factor, so joules is what we use more commonly throughout the world. We tend to use calories here in the United States. That SI means international system. Here is the conversion factor, so 1 calorie is 4.18 joules. So 1 calorie is about 4 times what a joule a joule would be. So you guys write that down. That's a conversion factor that you might have to we convert between. So here's what calorie is defined as. So a calorie is defined as the heat needed to change the temperature of 1 gram of water by 1 degree Celsius. So what we're saying here is, if I got 1 gram of water, I'll remind you guys, 1 gram of water is 1 milliliter of water, so I'm going to just get about a milliliter of water. So you guys can see, I put a milliliter of water in my hand. You guys can't really see it here, but it's not much water. Obviously, you guys know what's happening. Heat's going from my hand into the water. So if I measure the temperature of the water in the hand was initially, let's say, 27 degrees Celsius, and now it's going up to 28 degrees Celsius. What I would say is that absorbed 1 calorie of heat. Remember, 1 calorie is the heat needed to raise 1 gram of water by 1 degree Celsius. Now you guys would agree, I would imagine, a calorie is not very, you guys know that there wasn't much heat associated with that. And a calorie is a very small unit of heat. That's why when we're using calories to talk about how much energy a food item contains, here's what we're doing. So 1 food calorie, that is what we call 1 big C calorie, which is actually 1 kilocalorie. And those of you guys who remember the prefix is kilo means 1,000. That's the same thing as 1,000 small c calories. So you guys realize that whenever we're talking about small c calories, it actually takes 1,000 of those to make up 1 food calorie. And that's because the amount of energy in food is so much larger, right? You can imagine if we said a soda had 150 calories, if we use small c calories, we'd have to say it had 150,000 calories. So that's why we use a different kind of value when we're talking about food. So just make that note, small c calories, a very small unit of heat energy.
Items of food contain considerable energy. Under appropriate conditions, this energy can be released much more rapidly than it is in your body. To release the energy rapidly, a sample of potassium chlorate is melted with a burner, and a piece of food is dropped into the molten potassium chlorate. The food reacts fairly violently in an exothermic process that releases considerable energy.
So you guys, they used a chemical, potassium chlorate, which helps break down the food item. And you can see the energy given off in the form of light and heat. You can imagine the more light and heat given off indicates the more energy that was stored in that food item.
Here is a Cheeto. According to the nutritional information...
Okay, so guys, look at that. Hopefully you guys look at nutrition labels often when you guys are eating food items. So that was a Cheeto. You guys, you would probably agree, the number one thing you probably want to look at on a nutrition label is probably the calories. That's telling you how much energy is in that food item, and you want to know that because that's the energy that your body's going to store unless you guys expend it with physical activity. And I would ask, what do you think might be the next most important part of that nutrition label you might want to look at? I know some people say, oh, well, maybe the sodium or the cholesterol. All these things are important, but you know what I would argue? You probably want to look at the servings per container, because this is how different food producers kind of fool you. Like, let's say there's this bag of Cheetos, and you're like, oh, 150 calories, and then you can look up online and, oh, maybe I'd have to do about an hour of exercise to burn off the 150 calories associated with that bag of Cheetos. But in reality, you know what? When this says, and let's say a lot of times you're going to, you have a bag like that, and you might eat the whole bag in one sitting. But you see in reality, they're saying the servings per container is 2. You thought the whole bag of Cheetos was 150 calories, when in actuality, how many calories are in that bag of Cheetos? Well, that's 150 per serving, so if there's 2 servings, that's 300 calories. So that's oftentimes how food producers get away with making you think you're taking in more calories than you actually are. So I would look at those things. So anyways, question is, do you think Cheetos have a lot of calories or little calories?
According to the
I think you would agree, a lot of calories. That's actually a lot.
Provide 150 nutritional calories. 1 nutritional calorie is 1 kilocalorie, so each Cheeto can release about 7 kilocalories or 30 kilojoules of energy.
Look how violent that reaction is.
When a Cheeto is
Indication of
placed
how
into
much.
liquid potassium chlorate, the vigorous, highly exothermic reaction releases about 30 kilojoules.
So you guys remember, all matter has energy stored in it in the bonds between the atoms or molecules within that substance. And in this chemical reaction, it kind of broke down the food item, and all that energy that was once stored, it's called chemical potential energy, was released primarily in the form of heat. The more potential energy, the more heat or light that was released. So it's not surprising there was a lot of heat and light released, because you guys think about Cheetos. What's the big thing about Cheetos, right? Aren't they fried? They're fried in oil. Oil has a lot of fat. Fat has a lot of calories per gram. Compare that with the celery. Now you guys put the celery in that same potassium chloride. What do you guys think might be different? So I'm trying to get you guys to try to predict before you see something.
The celery reacts vigorously, but much less than a Cheeto does,
So
because there are
notice there
fewer
is a
calories
reaction.
in a piece of celery than there are in a Cheeto.
Not nearly
This
as
demonstration indicates
vigorous
how
as
much
the
energy
previous
is
one.
available from oxidation of foods.
And that's obviously why if you were on a diet, you would probably want to, satiate your hunger with celery than you would Cheetos, because you're going to have less calories, less likely to store that in the terms of, form of fat on your body. Okay, guys, this is going to be a little violent. I'm going to say, Warner,
When a
beware.
gummy bear, which is mainly composed of sugar, is dropped into molten potassium chlorate,
What do you guys think?
a reaction
It's gonna be
occurs
brutal, guys.
that
Turn away
produces
if you
carbon dioxide, steam, potassium chloride, and a lot of energy. The reaction is exothermic, which means
Ooh,
it gives
that's
off energy.
Its head was attached right there. Oh. And you guys can imagine a gummy bear, a lot of its energy, calories are going to come from sugars, right? Anyways, we normally do an activity, unfortunately we can't. Okay, now you guys, we're going to introduce, this is a very important term, specific heat. Okay, so, and you would understand this better if you had witnessed the activity. We'll have to do that in our live session. But specific heat is defined as the heat needed to change the temperature of 1 gram of a substance by 1 degree Celsius. Basically, what we're saying is every substance has its own unique, what's called specific heat value. That's why it's called specific heat. Let me just show you right here. You guys remember we were talking about, we were comparing the aluminum foil with the iron pan. Both absorbed the same amount of heat, but they rose in temperature at, a different rate, simply because of the matter it was composed of. So, for example, you guys will see the specific heat of water. It says it's 4.184 joules per gram degree Celsius. What that means is, when we say that, is we're saying it takes, you guys remember we learned about the calorie? Remember? And what do we say a calorie is? It's the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. So this is saying 4.18, but you guys remember the conversion factor, 1 calorie is 4.18 joules. So that is consistent with what we've seen before. So what that means is, let's use, for water, it takes 4.184 joules of heat to raise 1 gram of water by 1 degree Celsius. Now compare that with, like, for example, you guys look down here. You guys see for different water, but now look here. A lot of these are metals, aluminum, iron, lead. Now what do you guys notice about these values compared to that of water? Hopefully you guys realize they are much smaller. And what does that indicate? That indicates it takes a lot less heat energy. Just imagine like some iron or some lead or silver or gold, and you're heating it up. It takes much less heat in order to raise its 1 gram of it by a certain temperature. So a lower specific heat value, and that would explain why metals heat up so quickly. You guys think about on a hot day, you guys see a dime on the asphalt, a hot summer day. What do you guys think might happen if you go to pick it up? Isn't it gonna, it's gonna be extremely, extremely hot. Why? Because most metals have very low specific heat values, meaning when they absorb heat, that heat is immediately transferred to increased kinetic energy of the atoms or molecules, the temperature shoots up. Whereas you see with water can absorb the same amount of heat, and yet it's going to result in, meaning it has to absorb much more heat in order to have a significant rise in temperature. So what it ends up doing is it ends up storing that heat just in how it's the chemical structure of water. It ends up storing it rather than immediately resulting in an increase in temperature. Okay, so that's specific heat. We're going to be doing a problem or two using specific heat. So here's the definition again. Heat needed to change the temperature of 1 gram of whatever it is by 1 degree Celsius. Once again, why is it called specific heat? Because each substance has its own unique specific heat value, and I'd have to give you like a table of values. Other than for water, you guys should remember, what's the specific heat value for water? It's 1 calorie per gram degree Celsius. Remember that? It's easy, 1. And then if you had to convert it to joules, it'd be 4.18 joules. Okay, so the units are calories per gram degree Celsius. And once again, for water, it's 1 calorie per gram degree Celsius. once again, what does this mean? That's the amount of heat necessary to raise 1 gram of something by 1 degree Celsius. So does temperature, I'm going back, you guys remember, does temperature only depend on heat? You guys remember our scenario? No, it depends also on the type of matter, and it also depends on how much matter. So we're going to look at an equation that's going to incorporate all those factors that affect temperature and heat. So this is, you had already copied this down. This is just going back to what we had learned a few minutes before. So you guys, here is a specific heat formula. You guys write it down. It's very important. So what we find is the amount of heat absorbed or lost by a substance is equal to the specific heat of that substance. Remember, that's a specific value, times the weight or the amount of that substance times, and you guys, here's a Greek letter. This means delta. That means change in. Whenever you guys see that triangle, that means change in temperature. So you guys see how all those are incorporated together. The temperature not only depends on the heat, it also depends on the specific heat and the amount of the matter. Look at the units. The units, you guys, oh, here's an abbreviated way to show it. You guys, heat, in science we use a small q. We use a big C, or you might even use a big S, depending on who's writing the equation for specific heat. M, you guys could think for mass or weight, and then big T for temperature, more specifically change in temperature. Now look at the units that we would use for this. Remember, a specific unit that we use for heat could be calories. The specific heat units could be calorie per gram degree Celsius. Weight would be measured in grams, or mass in grams, and then change in temperature of degree Celsius. If you guys look at mathematically what's going to happen, notice whenever anything's on top and it's on the bottom, it'll cancel. So won't the grams cancel? Gram on top, gram on bottom, degree Celsius on top, degree Celsius on bottom. And what do you get? Calorie equal calorie. So if you guys forgot this formula, you guys could, just by looking at the units, you could ultimately come back to that formula, just making sure that the units end up working out. So that being said, guys, we're going to have to do a calculation. So I know it's been a while since we've done a calculation, but now in the thermochemistry, we have calculations. So here's the type of problem we can answer. How many calories are required to raise 5 grams of water from 10 degrees Celsius to 25 degrees Celsius? So, you guys, whenever you're doing chemistry problems, it's always good to visualize what it is you're doing. Otherwise, it's just going to be words to you. So when you guys are reading that problem, what should you guys be visualizing? When you visualize water, right? And how much water? I'm going to visualize 5 grams of water. And even if I didn't have a scale, if I had a graduated cylinder, I can measure out 5 milliliters, and that'd be 5 grams. This is actually, I would say this is 5 grams. It's actually probably too much. 5 grams. And you guys, what am I going to do? I want to raise the temperature from 10 degrees Celsius to 25 degrees Celsius. Obviously, so what do I need to do? I need to heat it up. What do I want to know? How many calories of heat is necessary to do that? See, by kind of visualizing what's going on, it's going to make the problem a lot more understandable to you. So I'm going to use my specific heat formula. First thing is, I got to decide what is it I'm trying to solve for. It says how many calories. So I'm looking for keywords, how many calories. Oh, calories is a measure of, and when I do the specific heat formula, I'd probably write it in my abbreviated fashion. Q is equal to C times M times T, okay? So basically it says how many calories. You know what? I'm looking for Q. So I don't have to rearrange this. It's already solved for Q, or arranged for Q. So I need the specific heat. It doesn't give me a specific heat value, but oh yeah, that's right. We're talking about water, you guys. That's when I asked you to memorize what's the specific heat value for water. It's 1 calorie per gram degree Celsius. Once again, that means it takes 1 calorie to raise 1 gram of water by 1 degree Celsius. How much water do I have? 5 grams. What is, and you guys got to remember, what's the change? That's the change in temperature. How much did the temperature change? It went from 10 degrees to 25 degrees. It went up by 15 degrees, right? You just subtract it. You guys now look at your units. The gram on top, gram on bottom cancels. Degree Celsius on top, degree Celsius on bottom cancels. What am I left with? Calories, which is what I want. And so now I just do the math. 1 times 5 is 5 times 15 is 75. What did I just figure out? It would take 75 small c calories of heat to raise 5 grams of water 15 degrees Celsius, 75 calories. All right? You guys, let's do another one. It says, what temperature rise can be expected if 15 grams of glycerol absorbs 210 calories of heat? Okay? So, once again, you guys, I'm going to use my specific heat formula. Once again, this would be a little hard to visualize because you're like, glycerol, what the heck's glycerol? Some of you guys might, if you guys ever read the shampoo bottles at your home, glycerol, it's actually a liquid that's added to shampoo to make it kind of soft and silky. Glycerol is actually, you guys, it's actually a clear liquid as well. Now it's actually more, it's actually a little thicker than actual water. So let's say I have 15 grams of glycerol, okay? And it's absorbed 210 calories of heat. Oh, you guys, there's something you should be able to tell me. Let's say you didn't really know much. I told you a little bit about glycerol. But can someone tell me something? Can someone tell me, as if you guys are here, as if I'm going to be hearing you guys. But I want you guys to think about, is there anything you guys could predict about glycerol just based on what you're seeing here? Let's say more specifically, look at the specific heat of glycerol. Glycerol has a specific heat of 0.314 calories per gram degree Celsius. Then I'd say, well, compare that to the specific heat of something you know. What do you know the specific heat of? Water. What's the specific heat of water? Remember, it's really easy to remember. 1 calorie per gram degree Celsius. Well, glycerol has a lower specific heat value. So what would you guys, you think about, what do you think you could predict about glycerol then? Well, if it has a lower specific heat value, doesn't that mean it requires less heat? Glycerol requires less heat in order for its temperature to raise. So you would expect glycerol to get hotter a lot faster than water. That's something that you would pick up just from this, even though we didn't have to do any calculations. So anyways, so the key is, you guys, you always want to look at your word problem, you know, trying to figure out what is it asking me to find. Notice it says, what temperature? So you guys think about it, in my equation, what am I going to be looking for? Aren't you going to be looking for this bad boy right here? So what I would suggest you guys do is algebraic manipulate it to solve for that first before you start plugging in values. So to get rid of C and M, if it's multiply, I do the inverse, which is divide. Okay, so what I do to one side, I do to the other. And so then that's what my temperature would be, okay? So it's the Q on top, so that's how much heat is involved. How much heat did it absorb? 210 calories, so I write that down, 210 calories. I divide that by C, which is the specific heat value for glycerol, 0.314 calories per gram degree Celsius. And then I also divide it by the mass of my glycerol, which is 15 grams. You guys cancel out anything that cancels. A calorie on top, calorie on bottom cancels. Gram on top, gram on bottom cancels. And what are you left with? You're just left with degree C, which is what you guys should be left with in terms of temperature. So now it's just a matter of using my calculator. So I punch in 210 divided by 0.314. And then what do I do with this, guys? You guys remember, look, it's on the bottom, so I do divide again, divided by 15. And I get 44.6. Now, lest you think you guys are done, you guys got to remember here, that's my answer 44.6 degrees Celsius. What temperature rise can be expected? Oh, yeah, you know what? In actuality, yes. You say that, because you guys remember, this is not really the temperature, it's the change in temperature. So how much would have I expected the temperature to rise? 44.6 degrees Celsius. Let's say the initial temperature was 10 degrees Celsius. How would I figure out what the final temperature is? Well, you guys see we use the specific heat formula to figure out what the temperature change would be. So if it was initially at 10 degrees Celsius, what do I do with 44.6? You know what? If it changes by, that means it could actually, we'd either add 44.6 or subtract 44.6, but we know we're going to add, and you guys have to look in the example there, what would indicate to us that this was, we would add it? You might say, oh, because it says a temperature rise, and you might realize heat, in this case, was being absorbed. It was being absorbed, so if a substance absorbs heat, you guys would expect the temperature to go up. So what I would do is add 44.6 to 10 degrees Celsius, and wouldn't the final temperature be 54.6? That's just if I asked that, but this is actually the answer that we were looking for. All right, guys, try to do it as quick and painless as possible. Until next time, we'll see you. Bye.